Welcome everybody on Zoom, welcome everybody in the lecture hall to this new week of information systems for engineers. So the part that we are in right now, database design theory, it's pretty tough. It's pretty tough, so you need to brace for this week and the next, but you know, we are going to take it slowly. I'm going to drive you through all this material. I'm going to try to give you intuitions for what we are doing. All of this material is actually what is typically taught in the bachelor's degree in computer science. So typically in the second year of a bachelor's in computer science. It goes deeper than what we are going to do in this course, but at least you will get some sort of overview and impression to what computer scientists are educated with, right? So this is really the advanced part of the lecture. Now you know the relational model, you know the relational algebra, you know SQL, how to create tables, how to design schema, how to query tables. Who is comfortable now with SQL, you know, querying around selection, projection from the Jupyter notebook? I see a lot of raised hands, very good. So continue to practice, very important. There will be exam questions asking you, we'll give you a data set, and then we'll ask you to write SQL queries, and then we ask a question that you have to answer through the SQL query, right? What we grade is the result of the answer to the question, not the SQL query itself. We'll give you the data set ahead of the exam, so you'll have all of the information before. You can even train with that data set before the exam takes place. So everything you'll have on exam day will be announced in advance, except the questions. But all the rest, the data set and environments will be known. It's going to be a computer exam, basically a Moodle quiz, except that the Moodle quiz for the exam is different from the Moodle quizzes that you have during the semester, because the goal of the Moodle quizzes in the semester is to make you think, right? Some of the questions might be formulated in a way to force you to actively think and double check and you know, critically think. In the exam, that's not the same. In the exam, it's a performance assessment. So the questions are targeted at evaluating your mastery of the material, which is completely different. All right, let's start then. Let's get started with what is on the menu today. Before, I'm going to quickly remind you of what we've done last week to make sure that it's fresh on your mind. So first, we've seen that this is really bad design. And the reason why it's bad design is that there's too much in this table. There are products with their prices, there are customers and customer information and orders and quantities and so on. This is bad. And we saw that it's bad for many reasons, because as soon as you want to edit the table, add or remove customers, add or remove products and so on, it's a huge mess. And then suddenly you have a lot to deal with. And that means if you're working with PHP and Python, that you're going to have to write a lot of code in order to deal with all of that. So this is not good. And we saw that this is the solution. You need to actually spread the data over multiple tables where every table makes sense, right? A table for the products, a table for the customers, a table for the sales and so on. And basically, there's even a fancy name for that. We call that the entity relationship model, this way of doing. So basically, the products and the customers are entities, right? And the sales are relationships between customers and products, right? It's a customer who buys such and such quantity of a product, right? Okay, for whom is it intuitive that we need to split across multiple tables with foreign keys pointing to primary keys? Okay, very good. So what we do now is the theory behind that. How, you know, intuitively you can say this is bad, this is good, but this is just intuition. I want to equip you with theory about that, to quantify and formalize why this is good or this is bad. So we looked into the first normal form. There are several of them. There's a second, a third, a fourth, a fifth, a sixth, the Boyce Code normal form, and so on. And we noticed that the first that we saw, that is a good practice, is what we previously called atomic consistency. So that wasn't even new to you. That's something that I already showed you in the very first weeks of the lecture. It's just that whatever we put in the cells of the tables are atomic values, strings, dates, durations, numbers, booleans, but atomic values. We don't put nested tables or anything. And whenever you have a normal form, it typically comes with a way to convert the tables that are not in that normal form into an equivalence table that is in that normal form. So in the case of the first normal form, if you have a table that is not in the first normal form, which is the case of the table on the left, you can force it to be in the first normal form by transforming it. And here the trick is to duplicate the values like phone, laptop, laptop. So everything that was atomic on the left needs to be duplicated as many times that there are rows in your nested tables, right? So this is the trick in order to normalize. That's called normalization. You normalize the table. It had nested tables, and you duplicate stuff in order to no longer have any nested tables, right? So this is not first normal form. This is first normal form. Okay. But then you're going to tell me, this is in the first normal form, right? So the first normal form is not enough to tell us if that's good or bad, because technically, if it's in the first normal form, then that's good, right? So there's more than just the first normal form. We need to do better than that. Okay. Something else that I told you about is the notion of a table universe. Many of the definitions that we'll see today, the notion of first normal form, the notion of functional dependency, the notion of super key that's going to come soon, the notion of candidate keys, also today's the notion of projection of functional dependencies, and so on and so on. These apply to tables. But in practice, you don't think of a single table. You think of all of the permissible tables that you have in mind when you design your schema. When you set up your online shop and you design the schema of your database, you don't think of one table. You think of all the tables that you're going to have in the future that are going to populate this schema, right? So the tables have a life, they evolve. So technically, when you say it's in first normal form, you don't mean just the table right now. You mean also in the future. You want to keep it in first normal form. Even if it changes, it's going to still be in the first normal form. The same goes for the functional dependencies. When you investigate functional dependencies, it's not just a functional dependency for one table. You also have in mind that the future tables will also have those same functional dependencies, right? So this is also important. So this is why we need this notion of universe. So the universe, it's not a formal thing. It's just the idea of whatever the designer of the websites with the relational database has in mind in terms of what they want to allow and not allow for the future. So it's really real life questions. Okay, so this is a table universe. And finally, this is where we stopped last time. I'm going to remove that thing that in the lecture hall hides the formula at the bottom by opening and closing the chat. There you go. So we finished on functional dependencies. What is a functional dependency? It's something that is defined with two sets of columns. One set on the left, one set on the right. In that case, it's A1, A2 that are the two columns that are on the left, and B1, B2 that are the two columns on the right. Of course, in real life, it's not going to be called A1, A2, B1, B2, right? It's going to be called price, name, product, first name, birthday, and so on, city. But here it's formal, so I'm just using this made-up column names. So we have A1 and A2 that functionally determines B1 and B2. What does it mean? It means if you know the values in one tuple, you know the value of A1, A2, then you also know the value of B1, B2. For example, if you know that A1 is foo and A2 is bar, then you know that B1 is true and B2 is 1. Or if you know that A1 is bar and A2 is foo bar, then you know that B1 is false and B2 is 1. All right? Let me give you a thought experiment to think in an equivalent way in the forms of playing a game. Imagine you play a game. I have a huge table, maybe with millions of rows in that table. And I picked at random one record, one row of that table, right? And I'm telling you, in that row that I picked, I'm telling you, this is the value of A1, this is the value of A2. That I'm giving to you. I'm telling you, for example, A1 is bar and A2 is foo bar. And now I'm asking you the question in that record that I have just one record in front of me that you cannot see, but I can see it. And I'm asking you, can you tell me the value of B1, B2? Well, if you have a functional dependency, the answer is yes, you can tell me. If I tell you A1 is bar and A2 is foo bar, you don't know what record I have. You don't know, maybe it's the first one, maybe it's the second one, right? If I tell you bar and foo bar, maybe it's this one. Maybe it's this one, right? So you don't know. But if I ask you for B1 and B2, you can still answer me because it's always going to be false here and 1 here, right? So this is what it means to have a functional dependency. B1 and B2 are functionally determined by A1, A2. This is what we saw last week. So that's an example in real life that the product functionally determines the price, meaning the price is a function of the product. And if I give you the product, you can tell me the price. For example, imagine I pick one tuple at random and I tell you that's a laptop. Can somebody tell me the price? It's ambiguous, right? There are several records where it's a laptop, but can you still tell me the price? Yes, it's 2000, exactly. And the reason is that the price is functionally determined by the products. Everywhere it's laptop, it's going to be 2000. Right. Here, it's not the case. The price does not determine the customer. Yeah. So in natural worlds, another way to put it is that the values associated with B, so all the attributes that are in the second set, they are a function of the attributes that are on the left-hand side. This means here that we could write formally that price is P of the product, where P is some function, right? Of course, it's not going to be a function like a logarithm of X multiplied by exponential of 1 over X squared or whatever explicit formula, right? There's no formula, but it's still a mathematical function in the sense that you're associating values with values, right? So phone is 800, laptop is 2000, HGTV is 1000. So there is a function that gives you the price. I have a quick comment on how to pronounce, this row right here. Product, row, price. I try to be careful and to always say product functionally determines price. When I see the arrow, I say functionally determines. You can also say price is functionally determined by product. Because there are arrows everywhere, it's very tempting to start taking shortcuts and, short-circuiting the name. And a lot of people, and me included, if I don't pay attention, we tend to start saying product implies price because the arrow it's not an implication, right? I might accidentally say imply, but you really, every time that's really functionally determines, right? So you need to be careful about that. If you want to speak casually, you can just say price is a function of the product. That's another way. Okay, who is ready to now continue with new things? There we go. All right, so this we saw last week. That's just a refresh. Okay, let's continue with super keys. Now that sounds super fancy, like some grand final of some TV show or whatever. So the super key, what is that? So we take a relational table, as always. We take a subset of the attributes, so some of the columns of the attributes, and we have a definition of when and when not this set of attributes is a super key. And it is a super key if this set of attributes functionally determines all attributes. It means that you have a functional dependency from A. A is that set of attributes, the subset of attributes. It functionally determines all of the attributes in the relation, everything. So that's what attributes are denote, is basically the whole set of all columns in the relation. In other words, if you know the values, I pick one record at random, I tell you the values in A, for all the columns in A, then you can tell me what tuple that is. Right? The values in A are enough to fully and unambiguously identify the full tuple. Right? So this is just, I love to put formulas around, right? It's just the same thing, just written in a fancy way. That if we take a subset of the attributes, now I called it K, it's just to make you used to not always using the same letters. It's a super key if for every two tuples, T in U, I take two tuples T in U, if T and U match on all attributes in K, so this is, T.K and T.K and U.K, this is an abbreviation for all of the values in the columns of K in T and U, right? So if T and U fully match on the columns in K, then T and U fully match everywhere. That's a super key. That's just the same thing that I said here, okay? So in other terms, if you want to fully check tuple identity, you need to check what tuple exactly you have. It's enough to give me the values in the super key. That's enough. Then I know what tuple it is. I don't need the other values, okay? Maybe we can try an experiment. So can anybody give me some super keys in there? So a set of columns that is a super key, that is enough to fully identify the tuple. Any idea? On Zoom too, you can participate. Yeah, can you speak in the microphone maybe, so that people hear you?
So we got an answer from Zoom, which is product.
Yeah, this is correct. This is correct. You can see the product fully identifies the entire tuple. How do we see that? Well, they are all unique. You see, all the values in the product column, they're all unique. They're all different. So if I tell you the value in product, that's enough for the entire record. If I tell you HDTV, then you know, let me show you. If I tell you the product is HDTV, then you know it's that record right here. There's only one record that is like this, and then you can tell me, okay, then price is 800, category is entertainment, and stock is 2. So we say that product is a super key of the table, okay? So this here is a super key. And in fact, this is also a super key, right? If I give you the product and the price, then I also know the entire row, right? It's actually trivial. Because if you already know the product, any additional information I give you, you don't care. You have the product anyway. That's already enough. So now I can tell you the product, and whatever else I can tell you, it's still a super key, right? Who understands that, right? So then the product, the price, the category, this is also a super key. If I give you all the values in the tuple, then you know all the values in the tuple, right? So the entire set of columns is also a super key, okay? This is not a super key. Why is that not a super key? So price is not a super key. Anybody? Yes, maybe the microphone, if you can bring the microphone to somebody raising their hand.
Because the value 800, it comes up twice.
Yeah. And why does it make it not a super key?
Because it doesn't identify it uniquely.
Yeah, it doesn't identify the tuple uniquely. For example, it could be phone or it could be HDTV. You don't know, right? So the price alone is not enough, right? Okay. Remember that we have sets, right? I'm assuming sets of maps, right? We never have duplicates in there. So this is why I'm saying that if it gives you all the values, then you know the tuple because there's no duplicates. There's only one tuple with the values. I think somebody on Zoom also gave the correct answer, right? In the chat.
Yes, we got two 800 values.
Yes, exactly. That is correct. That's exactly the idea. And we have a question on Zoom.
We have a question from Zoom. So the question is, so that means primary key is super key?
Yeah, that's exactly where we are getting. So let me answer quickly. A primary key is a super key. Yes, but it's not true the other way around. A super key is not always a primary key. So we still have extra work to do with the super keys. For example, I told you this is a super key, right? So everything here is a super key. So you could say, okay, that's a primary key. No, nobody would pick that as a primary key. What people pick as the primary key would be, for example, the products, right? So we'll see how we characterize a primary key amongst the super keys, right? So you are absolutely correct that a primary key is always a super key. It's just not holding the other way around, okay? But I'll come to that. We will arrive to the notion of first candidate key and then primary key. Yeah? Does it make sense on Zoom? Okay. So this is not a super key. This is also not a super key. Now it's also almost automatic, right? Why is it not a super key? Because we have twice the same value. For example, we have here twice high tech, right? So for example, it doesn't determine the price, could be 800 or 2000, I don't know, given high tech. And same for entertainment. I have twice entertainment. So if I tell you it's entertainment, then you don't know. Maybe it's an HDTV, maybe it's a 4K TV, you don't know, right? So it's not a super key, the category. Stock is also not a super key. We have 10 twice. What about that? So now I just modified the table and maybe I just sold a 4K TV to a happy customer and now I have 9 left. But now look closely. Something strange is happening because now we have unique values everywhere in that column, right? So technically, in this very specific table right here, stock would technically fit the definition of a super key, right? Who sees that, right? What's very important to understand here, think again of that universe of table. This is an accident. It's an accident. Here, it wasn't the case. So you have to be careful to be aware that sometimes you might have an accidental super key. It's unintended. It's just like by luck that it so happens that all the quantities are different. But think of yourself not knowing in advance what there is in there. You're setting up the website. Are you going to want to enforce that stock is a super key? No, probably not. There is no reason why you would like to enforce that the quantities are unique, right? So it might happen once in a while in specific tables along the way, but it's not going to hold for the entire universe of tables, right? So this is very important to be aware that you might have accidental super keys and accidental functional dependencies along the way. So you always need to ask yourself, is it really intended or is it an accident? In the case of products, that wasn't an accident. That was by design, that I wanted here to use the name of the product as the identifier of the product. Well, of course, if you're an online shop, you're not going to do it that way. You're not going to identify a product by name. You're probably going to identify with what's called a PID or whatever ID you have in your database of products, right? So it's called a reference typically with that you find in catalogs, or I'm sure you have seen that. But for my example, it was my intent that product is a super key, okay? But stock is only accidental. It might also happen that price becomes a super key accidentally, right? It might happen that at some point you just don't have any two products with the same price, but that's an accident. You have no reason why you would like to limit your database to forbid for having the same price for two products, right? Okay, so just be aware of that. It's a bit tricky sometimes that you might have accidental super keys. Now, at the exam, we are not going to be mean. We really try to come up with examples and tables that don't have these accidents, because otherwise that's mean, right? Then you end up with things that don't really make sense in real life. So we try not to do that. And what we say, there is a fancy formulation that we have, is that we are saying that this table right here that has an accidental super key, it's not a good representative of the other table. So this is not a good idea. This is not something we're going to have at the exam, this sort of table. This one, we could say that it's well representative of the universe, because the sort of functional dependencies you will find and the super keys you will find will in fact be intentional and be valid for the entire universe. For whom is that clear? Okay, very good. Okay, now I'm throwing all of this at you. These are 5 theorems. We can actually go into them. It's actually typically easy for many of them to prove in your head. Let's go to theorem 1, for example. Who agrees that attributes R, which is the set of all attributes in the relational table R, the set of all attributes is always a super key? Who agrees that it's trivial? Right? If you know all attributes, then you know all attributes, right? It's trivial. Who sees that? Raise your hands. Okay, I think a majority. Okay, so this one is really trivial. It's the definition of it directly. Now, if R is empty, what does it mean? It means we don't have any records. We don't have any rows. There's absolutely nothing. It's a set of maps, but it's an empty set of maps. So a subset of attributes, then, any of them, any subset of attributes is a super key of R. Why is that? It's almost a mathematical curiosity, right? Why is that? Yes? Maybe the microphone?
It's the same thing as theorem 1. A subset of an empty set is an empty set, which is the whole set, and thus theorem 1 holds.
Yeah, that's pretty much the idea. The key is actually here. If I want to express it formally, in the definition of a super key, I have this reverse A, right? So the reverse A, it's called a universal quantifier. It means for all, right? When you see this, so it's for all T and U in the extension. But what happens with a for all on an empty set, right? Here, the extension is empty. So I'm telling you for all T and U's that are in the empty set, so they don't even exist, right? You will never find them. And there is this mathematical convention that if you have this for all on an empty set, it's always true. You can write whatever you want after that. You can write that 2 + 2 is equal to 5 or whatever, even wrong. We don't care. The for all is always going to be true on the empty set. So this is why if the extension is the empty set, meaning that we don't have any records, this is trivially true by mathematical convention. So anything is going to be a super key. You can pick anything you want for K, the for all on an empty set will be true. So this is why if the table is empty, then everything is a super key. Of course, that's going to be an accident, right? Because it's just that you just opened your online shop, you don't have any customers yet, so it's empty and everything is accidentally a super key. Okay, the third one. If the relational table has only one record, means only one row in your relational table, then it is also true that any subset of the attributes is a super key. Everything is a super key again. But now the reason is a bit different. The reason is a bit different because now the universal quantifier, the for all, it's not going to be true immediately. So it's actually going to be true on the second line. Because if you have only one tuple and you pick any T and U in your set that is a singleton set, has only one value, then T and U will be the same, right? There's only one tuple to pick from. So if you pick two tuples from only one, then it's going to be twice the same, right? So this is going to be trivially true. T is always going to be equal to U no matter what that is, right? Something that implies true, it's always true. So this is why for a singleton, it's always going to be true, right? For whom is that clear? Okay. If you have only one row in your table and I play the game with you of telling you guess the row, then it's easy because there's only one. So you have no difficulty guessing which one it was, right? Okay. Now, theorem 4. If R, the relational table, has one attribute and at least two records, right? One attribute means one column, exactly one column. I don't have anything else than that column, and at least two records in there. Then these attributes, which is a singleton set, it's just a set with the one and only attribute that you have, is the only super key in the relational table. There's two things in there. First, that it's a super key. Second, that it's the only one. So why is that a super key? If you have a table with exactly one column, why is that column always a super key? Under set semantics, because on Zoom maybe, why in a table with exactly one column, that column is always a super key? Why is that? I think I see correct answers on Zoom.
Yeah, so we have the answers from Zoom. Because we cannot have duplicates.
Exactly. It's a set of map semantic. You cannot have duplicates. So if you have only one column and you don't allow duplicates, then all the values in that column are different, right? Since all the values are different, if I give you that value, then you know the tuple. Okay, it's that easy. Okay. But of course, there had to be at least two records. That's for the only part, because if there's less than two records, then the empty set would also be a super key, right? But with two records, the empty set is no longer a super key, because if basically the empty set being a super key means you know the tuples without any information. But if there's at least two tuples, there's no way you know which one it is unless I tell you which one it is, right? Okay. Theorem 5, it's a bit fancier. Now we take a relational table with two records, any number of columns, but two records. Then we can characterize the super keys of R. These are all the subsets of attributes where we have at least one of them on which the tuple differ. Because you need a difference, right? If I give you some of the values, you need a difference somewhere to tell apart the two tuples, right? If you only give me attributes where it fully matches, then you don't know which one it is. But if it includes at least one attribute on which the tuples differ, then it's a super key. So the goals of these theorems is just to develop your intuition of super key. If you take them again offline and think about them, it will develop your visual and your intuition of super keys. Okay? Okay. So who now feels like they could see a super key? If I show you tables, you can tell me if something is a super key. Right? Most of you. Very good. Okay. So we have the functional dependencies and we have the super keys, right? Two very important concepts, functional dependencies, super keys. But I define them on tables. Every time I give you one relational table and I told you, okay, on that very relational table, is this functional dependency holding, and is this subset of attributes a super key? Now we should extend that to table universes. What is a table universe? It's just a set of tables that fulfills the schema. So let's say, take a table universe, let's call it U. And they have the same set of attributes because again, it's the same schema, right? It's the evolution of a table under the same schema. So let's take two subsets of attributes that we call A and B. These are just sets of attributes. Then we can extend that notion of functional dependency on a universe. Basically, a functional dependency holds in a universe if it holds on all tables in the universe. Right? This is by definition. And the same for a super key. We're going to say that the set of attributes is a super key of the universe if it's a super key of all, each one table in the universe. Okay, so it's a natural extension to a table universe. For whom is that clear? Right, there is not really so much content in there. What does it mean in real life? What it means is, as a database designer, you're probably going to work on some example table, a representative table like the ones that I showed you earlier, knowing that in real life, there's going to be thousands of records in the table. But for your database design, maybe you start with that one. And so you're going to find some functional dependencies and super keys. You're going to avoid the accidental ones. So what you say is now they hold for that table, and now you decide, maybe not with a decree or something, because you would need to be a head of state for that, but you decide to make the decision, okay, these functional dependencies, I am saying right now, they will continue to hold for my entire universe of tables. I will make sure that they hold in the future. So this is why we say that we also define the notion of functional dependency and super key on a universe of table. It's just that we always want it to hold. These are constraints, right? Super key and functional dependencies. Okay. Okay. And now I have, this is something I already said and made you aware of, but I just added it in order to make it super explicit so that you are aware. It's that. And I very rarely do that, right? I very, very rarely put text on my slides because then you don't know if you're supposed to listen to me or to read the slides and so on. But here, I'm doing that because it's super important. When you design a schema, you can use a sample, representative tables. We don't have a functional accidental dependencies. But when you do that, you still have your universe in mind. You still have the future evolution of your table in mind when you do that. So you're thinking, what do I want to allow? What do I want my data to be like? And some functional dependencies may hold for a specific table, but not for the entire table universe. And you really, really, really make sure that you select the ones you want to enforce. And a counterexample of that a functional dependency that holds for a specific table, but not for the entire universe, that's this here. This is an example of an undesirable or accidental functional dependency that here holds for that table, but it's not your intent to make it hold for the entire universe. For the designer, it means you are not going to use that as an example. You are going to use that as an example, okay, to work on. For whom is that clear? Okay. So you see, this is why I seriously did it with plenty of text in there, probably the slide with the most text of the entire course. I don't know, but at least now I know that you know. Okay. So this table here is representative. This is a super key, and here this is a super key, not by intent. You see the difference? I just changed the 10 to a 9 over there, right? So if I change it to a 9, it's not by intent a super key, so I should not use that table. And at the exam, we are not going to give you tables like that to avoid this problem. Okay. So functional dependencies, super key, and we even saw functional dependencies and super keys on an entire universe. Who is following? Okay, let me check the time. See how much we have until the break. It is 10:49, so we still have a few minutes. Okay, so now I'm going to go to a third concept, the concept of candidate key. We are getting closer and closer to primary keys here, right? As probably some of you noticed. Okay, but for now, it's not quite yet a primary key, it's a candidate key. Okay. So here's the definition I'm throwing at you. I do it on a universe of table. Why? Because I'm designing my web shop, I'm designing my online shop, and I'm trying to think in advance of the evolution of my tables, and I'm trying to figure out my primary keys, right? So I'm going to build a candidate key on my universe. as a minimal superkey. So now I have to explain to you what minimal means, because a superkey is a set. What does it mean to be minimal on a set, right? So I need to explain that to you. But basically, it's that simple. You have your superkeys of your universe, and you look for the minimal ones. And when a superkey is minimal, then you call it a candidate key. Okay, so candidate key is a minimal superkey, and that's it. Now, I'm going to ask you, can anybody tell me what it means to be minimal? So I give you plenty of superkeys. I actually did right there, right? These are plenty of superkeys, right? 1, 2, 3, these are superkeys. So what does it mean to be minimal? Just making sure you understand formally what it means. Do we have anybody on Zoom? Maybe, oh yes, on Zoom.
Minimal attributes.
It goes in the right direction, but I need a precise answer. I need a very, very precise answer.
So we got another one. You cannot get a set of attributes that forms a superkey with fewer attributes.
Exactly, exactly. And I'm going to be even more precise than that, but this is the idea. So let me repeat the formulation on Zoom first. When you have a candidate key, it's a super key, you cannot find any other super key with fewer attributes. We are 90% of the way to what it means to be minimal. 90% of the way, we're almost there. Because now we need to understand what it means fewer. Let me give you, for example, a counterexample. Imagine that you have a relational table and it has 4 columns, A, B, C, and D, right? A, B, C, D. So now I'm telling you the superkeys in that table are A, B. So let me put it otherwise. AB is a superkey, and C is also a superkey, right? A and B together are a superkey, and C is also a superkey. C has only 1 attribute. AB has 2 attributes. So technically, you could say the superkey with C has fewer attributes than the superkey AB, right? AB has 2 and C has 1. Does that mean that AB is not a candidate superkey? You see where I'm going, right? With fewer, we just don't count. It's not just about counting and saying, okay, we have a superkey with 2 and another key has only 1, so that invalidates the one with 2. No, that's not how it works. When you say fewer, you mean that you really remove attributes from the superkey. So for example, if you have a superkey AB, and A alone is also a superkey. A is a subset of AB, right? It's a strict subset. A is a strict subset of AB. So if A is a superkey, then AB cannot be a candidate key anymore, right? For whom is that clear? Because then AB is not minimal in that sense. You can remove B and it's still a superkey, right? So with minimum, now I can be even more precise mathematically. You might think intuitively of minimum with numbers, right? The minimal number in a set of number, right? But here we mean minimum relative to set inclusion, right? So you know that it's a bit of abstraction capabilities, right? On numbers, you have a relationship between numbers that is smaller than or equal, right? 2 is smaller than or equal to 3, 5 is not smaller than or equal to 4. And you define minimum based on that comparison of numbers, right? Based on this smaller or equal. Something is minimal if there is nothing else that would be strictly smaller than it, right? This is what minimal means. But now we do a bit of a jump in our thoughts because now we don't look at numbers, we look at sets. So what relationship do we have in sets? We have inclusion. We can say that a set is included in another set. So what does it mean to say that you have a minimal set? It means that you don't have any other set that you consider that would be strictly a superset of that other set, right? Mathematically, it's the same. We just, in exchange of smaller than or equal for numbers, we use is included in for set, but the definition of minimal formally is the same, right? So again, I repeat, minimal is not about how many attributes there are in the set. It's about not being any strict subset of my candidate key, right? So let's look here. Now I probably have the slides actually. No, I will come back here. So why is that not a candidate key? Because I can remove attributes. You see, I can remove stock and category. It's still a super key. This is not a candidate key. Why? Because I can remove the price. I can remove stuff. For as long as I can remove stuff, it's not a candidate key. Now I cannot remove anything anymore. I have just product. If I remove something, it's the empty set, right? But the empty set is not a super key because there's 5 tuples in there. If I don't tell you anything, then you don't know what tuple it is. So the empty set is not a super key, and thus product is not only a super key, it's a candidate key because there is no strict subset of products that would be a super key. For whom is that clear now? Okay. So it's all about, can I remove any attributes in my candidate key? No, if it's a candidate key, you cannot remove any attributes without removing the super key property, right? You cannot remove any attributes without undoing the super key. Is there a question?
If HDTV was called 4-key TV,
yeah,
would you then need both attributes to form a super key?
Then product would no longer be a super key because you would have twice the same value, but price would still be 1. Price together with product because you would have 4K TV with 800 and 4K TV with 1,000, right? So in that case, product and price together would be a super key. Product would no longer be 1, but you would also need to prove that price is not a super key in order to establish that product and price is minimal, right? But be aware that if you start, adding 4K TV and so on, you're going outside of the intended design of the database, right? So it's more of a theoretical question, right? In real life, you wouldn't do that. But just for the example, yes, indeed, if you replace HDTV with 4K TV, then it's no longer a super key.
And a follow-up question, this is then a candidate key?
What is a candidate key? So product, if it's no longer a super key, then it can also not be a candidate key. Right? A candidate key has to always be a super key. If it's not a super key, then it's not a candidate key either.
Product and price.
Yeah. In that very case, that would be indeed a super key. It would be a candidate key, again, if you can also prove, so we also already proved that removing price, it's no longer a super key, but you also need to prove that removing products is not a super key. But you see it's the case because we have 800 twice. So you can see that price is not a super key either. So since product is not a super key, price is not a super key, and product price is a super key, then product price is minimal. You cannot remove anything in there, right? So then product price is a candidate key, right? You just need to be aware that it doesn't mean anything in real life on that example. But yes, absolutely. Yeah. Does it answer your question? Okay, and we have another one. Let me check the time to the break. 2 more minutes. So yes, I can answer the one more question.
Any 2 attributes that are a super key together, but not individually, they are always a candidate key?
Can you repeat, please?
Any 2 attributes that are a super key together, but not individually, they are always a candidate key?
Yes, so let me reformulate that to make sure that we understand. If you have a relational table with 2 attributes among others, A and B, and AB together is a super key, A alone is not a super key, B alone is not a super key, then AB is a candidate key. Does it make sense? I think it was your question, right? So the key part is you can have super keys with anything. You could also have 3 attributes in a super key. You just need to check, what if I remove an attribute, right? And if you can check that every time you remove an attribute, it's no longer a super key, then you have proven that it's a candidate key. Okay, that's what minimal means. Okay, let's take a break. I think you deserve the break, right? As I said, it's a bit tough, it's a bit formal. So let's take a break. I'll see you at 11:15, and then we'll continue with database design theory.